Okay, I'm going to trip over my wire, aren't I? Section 3, Chapter 7, Section 3. Triangular form. We are going to be using our matrices with systems of equations to help us solve. If we have a system, this has three variables, x, y, and z, and if I have it where the first equation has all three variables, the second has just the last two, and the third has just the last one, we call it triangular form. And if it's in triangular form, we know what the last variable equals, and we could substitute back into the second and get two variables, and then we can substitute back into first and get all three variables. So the idea is, if I have a system in triangular form, it is very easy to solve. I know what z is. Y minus 2 times 3 must equal negative 7. So y minus 6 is negative 7. Y equals negative 1. Come back to the first. X minus 2 times my y plus my z. What is my z? 3 must equal 7. So x plus 2 plus 3 equals 7. X plus 5 equals 7. X equals 2. I have my ordered triple. 2 is my x, negative 1 is my y, 3 is my z, and I have it solved. Of course, triangular form is not going to be very common all on its own, and so we are going to expect to have to put it in triangular form. Gaussian elimination. In reality, this is the same thing as the elimination we have done since Algebra 1. When I have a system of equations like this down here, I can interchange any two equations in the system. There's nothing magical about the order they have them or important about the order they have them. If it's more convenient for some reason, I can switch the order of those equations. That's what number 1 says I can do. Number 2 is I can multiply or divide, and usually we think of multiplying by a fraction instead of dividing, but it's the same thing, one of the equations by any non-zero number. And why would I do that? For the elimination method. I multiply it by something so that when I add them together, it eliminates a variable. So we really have done that idea before. And then we combine it with number 3, where we add a multiple of one of the equations to any other equation in the system. And that's where it eliminates something. But in this case, when we multiply an equation by a number, we're actually just going to use that answer to add to another equation without changing the one we multiplied by the number. So that original equation is going to stay. We're just going to use the answer to it to add to another equation to eliminate. So we're not actually going to change both equations. So let's try to solve this system by putting it into triangular form, and then we can back substitute. And triangular form has these characteristics. There is not only 3 variables in the first equation, but the lead coefficient is 1. The lead coefficient is 1. The lead coefficient is 1 every single time. And in this one, the x has been eliminated, and in this one, the x and the y has been eliminated. That's our idea that we go for in order to get something into triangular form. So as I look at this, hey, that first equation is just what I want. I have a lead coefficient of 1 and everything is there. So it looks good. On this second one, I want to eliminate the 3. So what would I do to eliminate the 3? How could I use the first equation to eliminate this 3? Multiply it by negative 3, and I can eliminate this 3. It's just elimination like we've done before. So how we write it is I'm going to take negative 3 times row 1 and add it to row 2. So on this step, this first one, even though I am going to use it, I don't really change it. I am just going to use the answer to that multiplication. Negative 3 times row 1, add it to row 2. Well, negative 3x plus 3x, gone. 6y, I multiplied everything by negative 3 here. 6y plus, minus 5y is 1y. Negative 3z plus z, negative 2z. Negative 21 plus 14, negative 7. Now I'm going to recopy the next row. 2x minus 2y minus z equals 3. I have my new system where I have eliminated that x variable on row number 2. And in this case, I have a 1y. If it wasn't a 1, let's say it was a 2, that would be where I would divide everything by 2 or multiply everything by 1/2. So I could make it a 1. To make 1s, that's when we do our dividing or multiplying by a fraction. So I'm going to work now on row 3. I want to get rid of this x term. Well, what could I do with that first row so that I could add it to this last one and eliminate that 2x? Multiply negative 2 times row 1 and add it to row 3. Now, even though I'm using this first row, I don't change it. X minus 2y plus z equals 7. Y minus 2z equals negative 7, because I'm not touching that row at all. Now I'll do that step 2 and 3. I'll multiply this by negative 2, add it to the last one. Negative 2x plus 2x, 0. 4y minus 2y, 2y, multiplied by negative 2. Negative 2z minus 1 more, negative 3z. Negative 14 plus 3, negative 11. Did I do my math all right? Okay, so the next thing is I want to eliminate this 2y. Remember on this bottom one, I want my x's and my y's gone. So if I want to eliminate that one, we'll come right above it. I could multiply the second equation by negative 2, and if I added it to the third, it would cancel it out. So that's my next step. Negative 2 times row 2, hey, I forgot my 1 up there. Negative 2 times row 2, and add it to row 3. So here will be our answer from doing that. First equation, not even using. Second equation, even though I'm using it, I just recopy it. And now I'll do that math of negative 2 times row 2 and add it to row 3. Negative 2y plus 2y, 0y's. Let's see, 4z minus 3z. Z, that was convenient. Negative 2 times negative 7, so 14 minus 11, 3. And in this case, I have automatically, I got my 1's here and my 1's here. What did I say? If I didn't have a 1, let's say I had a 7, what would I do? Multiply by 1 over 7 and everything, or divide by 7 on everything. That's how I get my 1's. But this one came out perfect. So I have triangular form. Now I'm not going to finish this out, but in order to solve, I would then substitute, and I think this may be the same equation. X minus 2y, y minus 2z, it is, isn't it? And then z equals 3, it is. So what did we get the last time? We practiced on it back here. It'll be the same answer if we did get in, 2, negative 1, 3. So if we substituted back in, 2, negative 1, 3, and we have solved it. This is called Gaussian elimination. Performing those elementary row operations is what those things are called. So we'll go through a series of steps to get it into triangular form. Solve this system. Now they happen to give us a hint. It's going to be a no solution system, but let's try it out. Well, row 1 is just what I want. Row 2, how could I eliminate my x, my negative x here? Just add the first one and the second one together and it would eliminate it, right? So all I need to do, and we're going to keep track of what we've done here, row 1 plus row 2. That's all I need to do. So I'm going to write my new system. The first equation is just how I like it. Don't need to touch it in any way. The second equation is going to be my answer from adding row 1 and row 2. Well, 0x's, negative y, negative 4z equals 7. Row 3, just copy it. We only do one operation per step. Now, I don't want a negative y, I want a y there. So how can I get a y? Multiply by negative 1. I'm just going to take negative 1 times row 2. That is the step I am doing here. x minus 3y plus z equals 4. Negative 1 times row 2, y plus 4z equals negative 7. And I didn't touch the last row, so it just gets copied. Okay, so my equation 1 and equation 2 are just how I like them. Now I need to eliminate the x and then the y in the last one. Well, to get my x's, I go back to the top. What could I multiply row 1 by? Negative 5 times row 1 and add it to row 3. First equation we will use, but we don't change it in our system. Second equation, don't change it. These two are already done. All right, negative 5x plus 5x, 0 x's. So that'd be 15y minus 13, 2y. Negative 5z plus 13, so that'd be positive 8z. Negative 20 plus 8, negative 12. Okay, I need to get rid of my y's. How am I going to get rid of my y's? Negative 2 times row 2, add it to row 3. That will do it for me. Gaussian elimination takes a few steps where you simply copy carefully so you don't miscopy anything. All right, negative 2y plus 2y gone. Negative 8c plus 8z. 0 is all that's left on the left side, everything eliminated. Negative 2 times negative 7, that would be 14 minus 12, 2. Does 0 equal 2? No. False statement, no solution. You may remember from previous classes where we had that situation before. When I get that false statement, 0 equals 2, something like that. There's no solution to this one. Instead of using the big system of equations, we are going to do matrices. It just saves us time. Essentially, we're eliminating the x and the y and the z. And we are writing it in what is called the augmented matrix, where the first three values are the x, y, and z coefficients. And the last column are the constant solutions out there. So you can see that left system of equation, the numbers match in that augmented matrix, it is called. If they talk about the coefficient matrix, well, the coefficient matrix is simply the coefficients of the x, the y, and the z. So the augmented matrix includes everything, including the answer constants on the right side. The coefficient matrix simply includes the coefficients. And when we get this matrix, this augmented matrix, into triangular form, then we say it is row echelon form of a matrix. It's the same deal. Row echelon form, let me make a matrix here. I have 1x, 2y, 3z equals the number 4. 0 x's, 1y, 2z equals the number 5. I'm just making up the numbers. 0 x's, 0 y's, 1z equals the number 6. That is called row echelon form. It is the triangular form match when I have a system. It's the same thing as triangular form. Rows consisting entirely of zeros, if there are any, need to be at the bottom. We may have everything goes to 0. Well, so that needs to be written at the bottom. Rows consisting, number 2. The first entry in any row with non-zero entries is a 1. The first entry needs to be a 1. The 1x up there, the 1y there, the 1z there, so it's just like having a 1 coefficient. Number 3, the column subscript of the leading 1 entry increases as the row subscript increases. What they mean is it moves over in a diagonal pattern. As the row subscript, as I go from row 1 to row 2, my column subscript needs to increase from column 1 to column 2. That's what they are saying by this number 3. Everything just moves over as it comes down. So it's triangular. Elementary row operations, that is what they are called when we are talking about a matrix. It's the exact same thing as the Gaussian elimination steps. It's just a different term. It's exactly the same thing. Interchange rows, multiply all elements by a non-zero number, add a multiple of a row to another row. Same things. We're just going to be doing it with a matrix. So let's try it out. They say find row echelon form. That's triangular form. But I first need to turn it into an augmented matrix. So my first row, 1, -1, 2, -3. 2, 1, -1, 0. -1, 2, -3, 7. And then I'm just going to run across, and my first row is just what I want. I start with a 1. My next row, I want to eliminate that 2. So what am I going to multiply row 1 by to add to row 2? -2 times row 1, and add it to row 2, and that is going to give me, well, the first one I don't change. 1, -1, 2, -3. Now I'm going to do my math. -2 plus 2, 0. -2 here, and if you want to, you may even want to throw the number in front that you're doing. 2 plus 1, 3. -4 minus 1, -5. 6 plus 0, 6. And the last one I copy. -1, 2, -3, 7. Okay, the next thing I want to do, I want to get this 3 to be a 1. What will I do to make that 3 a 1? Divide everything by 3, or multiply by 1/3. So I'm going to write it as 1/3 times row 2. That's all we're doing here. 1/3 times row 2. So the first one, recopy. 2, -3. By 1/3, let's see, 1/3 is 0, 1/3 of 3 is 1, -5/3 and 2. Just multiplied everything by 1/3. -1, 2, -3, 7. Okay, my row 2 is just what I want. So I'm going to come to the bottom. I want to eliminate that -1. Looking above, what can I do? Just add it to which row? Yeah. Row 1 plus row 3. That's all I'm doing on this step. 1, -1, 2, -3, 0, 1, -5/3, 2. Just be real careful with your multiplication and addition is really all it is here. So adding these, 1, -1, 0, -1, 2, 1, 2 minus 3, -1, -3, 7, 4. Okay, I want to eliminate this 1 now. Looking above, how can I eliminate that 1? -1 times row 2, or negative of row 2, and add it to row 3. Exactly right. 1, -1, 2, -3, just gets copied. Second one, I'm done too. -5/3, 2. Now I need to do negative times this row. I'm taking a -1, I don't know, maybe you want to write it wherever you want to write it. -1 times that and adding it to the end. Well, 0, 0 still gives me 0. -1 plus 1, 0. +5/3 minus 3/3, is that 2/3? -2 plus 4, 2. I need a 1 now in that location. What can I multiply by to give me a 1? The reciprocal, 3 over 2. So my next step, I'm just going to go 3 over 2 times row 3. All right, 1, -1, 2, -3, 0, 1, -5/3, 2, and now just multiply everything by, what was I doing? 3 over 2 times 0, still 0. 3 over 2 times 2/3 is 1. 3 over 2 times 2, 3. There is row echelon form. It's just like triangular form. Now they want us to solve the system, so let's finish it out knowing that z equals 3 is what that line means right there. And this is 1x, x minus 5/3 times z, which is 3, equals a 2. That's what that row means. Well, that would be x minus 3's would cancel. X minus 5 is 2, so x is 7. Okay, well, I've got those two. Now I'm going to go back to row 1. Thank you. That is a y, not an x. Row 2 does not have an x, 0 in the x, 1y. Now I'm going to go back to row 1. 1x minus my y, what did we get, 7? Plus 2 times my z, where's my z, 3? Equals a negative 3. That's what this row says. So what do we have? X, 2 and 3 are 6, negative 7 plus 6, negative 1 is negative 3. X equals negative 2. Negative 2 in my x, 7 in my y, 3 in my z. I have solved my system. I used an augmented matrix because it saved me time with the x, y, and z's. That's what it's doing with the augmented matrix. Same things. Elementary row operations are Gaussian elimination is what they are. So what's up on infinitely many? Okay. Well, my row 1, I like that row 1. Not going to interchange it. We haven't seen any that we've had to interchange, but don't forget that. You can interchange. When would I want to interchange? Let me give you a hint. Let's say I had that. What might I want to interchange? Yeah, just switch the first and the third, and then I've got a 1x, just like I want. I mean, there's a reason why I might want to interchange. So that first one I like. But I want to eliminate this 2. So, need to copy it first. 2, 1, 4, 8. How am I going to eliminate that 2? Say it again. Negative 2 on what? Row 1. Add it to row 2. So 1, 1, 1, 3 doesn't change. The last one doesn't change. Sometimes I will go through and copy the ones that I'm not touching. Keeps me from making a mistake and changing one I don't want to. So I'm doing negative 2 times this one. Negative 2 plus 2 is 0. Negative 2 plus 1, negative 1. Negative 2 plus 4 is 2. Keep track of my math. Make sure you're awake out there so I don't make a mistake. Negative 3 and negative 6 and 8 is 2. Okay, you tell me the next thing I want to do. That negative 1 needs to go to a 1. So how will I do that? I'll just do negative 1 times row 2. And first row, 1, 1, 1, 3, not touching. Last row, 1, 2, negative 1, 1, not touching. Negative 1 times this one will just change all the signs. What's the next thing I need to do? Top row by negative 1 and add it to row 3. It will eliminate that last one. 1, 1, 1, 3. 0, 1, negative 2, negative 2. Multiplying negative 1 plus 1, 0. Negative 1 plus 2, 1. Negative 1 minus 1, negative 2. Negative 3 plus 1, negative 2. What's next? Negative 1 times second row, add it to row 3 so I can get rid of that 1 on the bottom. So negative times a row 2, add it to row 3. And 1, 1, 1, 3. 0, 1, negative 2, negative 2. So, well, 0 plus 0 is still 0. Negative 1 plus 1, 0. 2 minus 2, 0. 2 minus 2, 0. What does this last row mean if I wrote it as an equation? 0 equals 0. Is that true? Yes, it is. There are infinitely many solutions, but we don't stop at this point and say, oh, infinitely many solutions. We say, let's make that last variable z just z. And we are going to work our way backwards, writing our solutions in terms of z. So if I come here to row 2, that's 1y minus 2 times z equals negative 2. And I'm going to solve for y. Y must equal 2z minus 2. I isolated the y. There's my y. 2z minus 2. And then we're going to back up to the first row and take the same idea. I have 1x, x, plus 1y, and what is y? 2z minus 2. Plus 1z, and what is z? Z. And it equals 3. I'm substituting z for z, 2z minus 2 for y, solving for x. Well, x equals 2z and z are 3z, which if I moved over, negative 3z. Add the 2, plus 5. That's what x is, negative 3z plus 5. How is that useful to me? Here's how it's useful. I can generate any ordered triple that is a solution to it. If I decide I am going to use, let's use 1 for z. 2 times 1 is 2, minus 2, 0. 1 here, negative 3 plus 5. 2, 0, negative 1 is one of the infinitely many solutions of that. Pick another number for z, and you get another set of ordered triples that are a solution to it. So this allows me to generate all of them. It's possible to say, instead of z as z, let's use x as x. Or you could use y as y and do the same idea. But because we're doing this reduced echelon form, where it's set up to, if I know z, it's easy to substitute, that's why we're doing it this way. We pick z as z. Infinitely many solutions, solve the system. Notice it has how many variables here? There are 4 variables. So we can leave behind, we went to 3 unknowns in Algebra 2. Hey, we can pile it on now. If I have this as an augmented matrix, 1, 2, negative 3, 0 for my w, and then there's my negative 1. 2, 3, negative 4, 1, negative 1. 3, 5, negative 7, 1, negative 2. Get your calculators out. Let's enter this augmented matrix. So we are going to go to our matrices, we are going to edit, and I'm going to edit matrix A. Matrix, go over to edit, and I'm selecting matrix A. Now what's the order of that matrix? That's a 3 by 5. And then stick them in. Once you have it entered, you have to quit out. And then we're going to go back to our matrix. We want to do some math on a matrix. So I'm going to arrow over to math. And if you go down far enough, you will find reduced echelon form, or row echelon form. I forgot the name of it. Was it called row echelon? I think it was called row echelon form. Row echelon form, sorry. Enter. I want to do row echelon form. Now I need to go back, matrix, matrix A, enter. I'm going to close parentheses to make it pretty. And it says, okay. Oh, you know what I should have done? Answer is fractions. Second, just a minute. Matrix. Matrix, there we go. I want to do math. I forgot the choice number. 9? Oh, A. Row echelon form of, is it already on second? Second matrix. There we go. Matrix A. Go back to my math and tell it choice number 1 and make it fractions, please. Okay? Well, you're going to have to arrow over. Let me save part of it. There's the first part. Where'd my calculator go? So second, parabolas, ellipses, circles, hyperbolas, all our, which, but we didn't. All our conic sections, I have fine that goes through those. Invert my matrix A, multiply it by my matrix B, in case there are any fractions hanging around. Four, is this the same answer as you got? C. So the equation ax squared, 4x squared, plus bx minus 6x, plus c minus 5. That should be a parabola